Hello everybody. In this video we're going to talk about how to calculate the pH of a weak base solution. So first of all, there's actually three major types of weak bases. I forgot to put the first version, which let's call it number 0, which is actually the weak bases that are metal hydroxides that are not from group 1 or from the group 2 metal hydroxides. So let's call them metal hydroxides that are not part of our list of strong bases. For example, something like iron hydroxide, let's say iron 2 hydroxide, would be something like this, and that is a weak base. In addition to those, we also have the weak bases that are made from the conjugate bases of weak acids. So for example, if you take acetic acid, the conjugate base of that would be categorized as a weak base as well. Similarly, we have the cyanide anion and the hypochlorite anion, all of which are conjugate bases of weak acids, and they fall within the category of weak bases. The third type of bases that we're going to be discussing are amine bases. These amine bases have a structure that is very similar to that of ammonia. If ammonia, you guys remember, has nitrogen as the central atom, and then the three hydrogens are covalently bonded to it, and we have a lone pair of electrons available on that nitrogen that enable it to be a proton acceptor, right? So the amine bases are going to have a structure that is very similar, but typically what's going to happen is that one or two or three of those hydrogens are going to be replaced with something else. For example, in the molecule methylamine, which is what we have here at the bottom, we can see that one of the hydrogens has been replaced with what we call a methyl group here. So I'm going to go ahead and circle this, CH3. That is called a methyl group, and that makes it methylamine. That's the same thing. That molecule is written here, its formula, as NH2CH3, where basically we have replaced one of the hydrogens, so we only have two hydrogens as opposed to three, and the third hydrogen has been replaced with a methyl group. Some of the other amine bases might have two methyl groups or maybe three methyl groups instead of the hydrogens. Or we might replace the hydrogen with something called an ethyl group. An ethyl group will be written as CH2CH3. So if I had replaced a hydrogen with a CH2CH3, then that would be an ethylamine. And again, we could replace one or two or three of the hydrogens with ethyl groups. Those amine bases, the key thing is that they need to have a lone pair of electrons available to bind to hydrogen. Otherwise, they could not act as proton acceptors. Another amine base that I want you guys to remember is this one right here. This one is called pyridine. This one has a slightly different structure, which I will show you in the next slide. But I do want you to remember that this is a weak base as well. This table contains a number of weak bases, starting with ammonia, which is our primary example of a weak base. This is pyridine, which is the one that I mentioned in the previous slide that you should remember. Look at the difference in the structures. Of course, pyridine has a completely different structure. It's a cyclic structure, but the main feature of that amine base is that it has the nitrogen with a lone pair available to be able to accept a proton or bind a proton. Another example of a weak base is hydroxylamine, where we have replaced one of the hydrogens from ammonia with a hydroxyl group. So this is still a weak base, and we're still basically looking at that nitrogen having that lone pair of electrons. There's another example here of a weak base, methylamine, which is the same one that we had in the previous example. The other thing that I want you to see is that the conjugate acid of these weak bases is basically the same molecule after it has accepted another proton, right? That proton comes and binds to that central nitrogen wherever that lone pair of electrons was. So once we have this that hydrogen bonded to the center atom, that molecule can no longer accept another proton. So that makes it a conjugate acid, and it therefore would not be a base anymore. Go ahead and remove that if I can, which I don't know how to. Never mind. All right, the next thing that I want you to see in this table is the fact that each of the bases is associated with a Kb value. The Kb is going to be the equilibrium constant expression for the dissociation of that base. And the value of that Kb tells you information about the strength of the base. The larger the Kb is, the stronger the base. So between the first and the second one, this ammonia would be a stronger base, right? Because it has a larger Kb. All right, so clicker question for you guys. Which of the following is not a weak base? And go ahead and pause the video and think about it on your own. Dun, 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 dun. Okay, so hopefully you were able to look at this and at least be able to recognize that A and C, at the very least, are weak bases. Why? Because this one, A, is basically a conjugate base of a weak acid, and that was one of our categories of weak bases. Conjugate base of a weak acid. All right, so that was not the answer. Same thing with this one, right? This is a conjugate base of a weak acid. Oh well. All right, so I'm hoping that you were able to recognize a couple of things. First of all, remember that, oops, oh my goodness. All right, so in order to answer this question, the first thing that we need to do is to remember what are the various types of weak bases. One of the types that we mentioned were the conjugate bases of weak acids. Sorry, I can't write. Weak acids. And in that category, let's call it category number 1, we have at least 2 of those here. The first one, this hydrogen carbonate, is actually the conjugate base of carbonic acid. Similarly, our cyanide ion here, it's the conjugate base of hydrocyanic acid. The second set of bases that we mentioned just a little bit ago are the amine bases. Those amine bases have a structure that is similar to that of ammonia, meaning that they're going to have a central nitrogen, and then they're going to have at least 3 things that are attached to that nitrogen, which leaves a lone pair of electrons available to bind. And right now I'm just going to put R on these 3 bonds to indicate any kind of substitute on that group. In this particular case, we actually have at least one of those amine bases. This one right here is one of those. And basically, hopefully, I'm hoping that you're able to recognize the fact that we have a nitrogen, which is going to be our central atom. And in this particular case, we have 3 different ethyl groups that are attached to that nitrogen, right? So in this case, the R groups are going to be CH2CH3, an ethyl group. And we have 3 of them, which leaves a lone pair of electrons on that nitrogen for it to be able to act as a base. The last one right here is also an amine base. This is the one that I had you remember. This is pyridine, right? It has a different structure, but it still has that nitrogen with a lone pair of electrons available to accept a proton. In this particular case, the last thing that we have left is the answer. This one right here, even though it looks like an amine base, in fact, it has nitrogen and it has hydrogen and it has methyl groups that are also attached to it. But if you notice, we actually have a total of 4 things that are attached to that nitrogen. Let's go ahead and write it out. Nitrogen, which is this guy. Then we have a hydrogen. So let's go ahead and put that hydrogen here, if you don't mind. And then we have 3 methyl groups, 3 of them. So I'm going to put one here, CH3, one here, CH3, one here, CH3. If you notice that nitrogen has an octet already, there's no longer a lone pair of electrons on that central atom. Therefore, that substance is complete. It could not possibly accept another proton. And in fact, that makes it a charged molecule, which could act as an acid, but it could not act as a base. So this was a bit of a tricky question, but hopefully you understood the way that I solved it. All right, so we need to learn how to be able to set up an ice chart for a weak base so that we are able to calculate the hydroxide concentration at equilibrium. And from that hydroxide concentration, we then would be able to calculate the pH. To be able to set up the ice chart, we need to know how to write the equation, right? So for any particular weak base, we're always going to add water, because remember that a base is a proton acceptor and that proton needs to come from somewhere. In this case, it is going to be accepting a proton that comes from water. So water as a liquid has to be one of our reactants. On the product side, what we're going to have is the conjugate acid of the base, meaning the base once it has gained or accepted a proton, and we're going to have what's left of the water after it donates the proton, which is a hydroxide ion. This is the equation that you need to write whenever you have a weak base. From here, we would go and set up our ice chart, our initial, our change, and our equilibrium underneath. And of course, anytime that we do an ice chart, we follow with an equilibrium constant expression. In this particular case, with a Kb, which is the equilibrium constant expression for a base. And that's going to be equal to our product concentrations divided by our reactant concentrations. Now, since the water is a liquid, pure liquid, it is omitted from the Kb equation. And that it is. All right, so first example, write the reaction and the Kb expression for ammonia. So ammonia, you guys should know this, is NH3. That is our weak base. We need to write the Kb expression. So to be able to do that, we're going to write a reaction, which means that that ammonia is going to act as a base by accepting a proton from water. We need to have water, and let's go ahead and put our phase as a liquid to remind us the fact that that water is not going to be part of the equilibrium. What are the products of this? Okay, we said that ammonia is acting as a weak base, which means that it is going to be accepting a proton, basically forming the ammonium ion, NH4+. And then our other product is going to be whatever is left from the water after it has donated a proton, which is basically our hydroxide ion. That is the equation. Don't forget to use the double-sided arrow to indicate that this is an equilibrium process. From there, now we can write our Kb expression, which is going to be equal to our products, NH4+, times the hydroxide ion concentration, divided by the concentration of ammonia, NH3, and that's it, because we omit the water. Now I'll go ahead and mention that you could have also written this equation by just using the letter B for base, that would have been okay, plus water, forming HB plus or BH plus, I don't care, as long as you had an extra hydrogen and a charge associated with that, and then hydroxide ion. All right, the second example is to write the reaction and the Kb expression for the acetate ion. The acetate ion is CH3COO minus. That acetate ion is going to be acting as a weak base, and that means that it is going to react with water and end up accepting a proton from water in order to form acetic acid, CH3COOH. And what is left is the water after it has donated a proton, meaning that we're going to have the hydroxide ion. From there, we're going to write our Kb expression, which is going to be equal to the concentration of acetic acid, which is our first product, CH3COOH, times the concentration of hydroxide ion divided by the concentration of the acetate ion, CH3COO minus. That's it. Remember that the water is a pure liquid and will not be included in your equilibrium expression. All right, the next example is to calculate the molarity of an aqueous ammonia solution that has a pH of 11.17. We are also provided with the Kb value for that process. All right, so how do we approach this problem? All right, first of all, we know that this is ammonia. We know that ammonia is a weak base, right? All right, we also know that we have the pH of the solution. The pH is associated with the acidity of the solution at equilibrium. From that pH, we can do two things. We could either take it and find the value of the pOH. Once we have the value of the pOH, we can then use that to find the hydroxide ion concentration at equilibrium. And once we had the hydroxide ion concentration at equilibrium, we could use that to go and find the molarity of the ammonia. And for now, let's just go ahead and leave that here to remind us that we actually do know some information about the hydroxide ion concentration. But let's go ahead and get started. We have a weak base. We know that to be able to do an ice chart for a weak base, we're going to take that weak base, ammonia, NH3, and we're going to react it with water. We always have to do that, and remember that that water is a pure liquid. From there, we're going to have our product. The product is going to be the ammonia after it has accepted a proton, forming the ammonium ion. And then what is left is the hydroxide ion that came from the water. We're going to set up our initial concentration, our change, and our equilibrium. The initial concentration, we actually don't know it. We're going to go ahead and call it NH3, initial, with a little knot. What else do we know? About the products, we know that initially there's going to be 0 of them because the ammonia has not yet reacted. And we also know that water is a pure liquid, and so it's not going to participate in the equilibrium, and we can cross it out. The next thing is that we're going to set up our changes. We don't really know anything about the changes, so we're going to use X. For the reactants, that's going to be negative X because they're being used up. And for the products, that's going to be positive X because they are being formed in this process. And then after that, all that we're going to do is to add everything in the column, which means that our equilibrium concentration is NH3 initial minus X. Well, here we're going to have 0 plus X, which is X, and 0 plus X, which is X. We're then going to set up our Kb expression, because anytime that we do an ice chart, it goes with a K, equilibrium constant expression, in this case Kb, and that Kb is going to be equal to the ammonium ion concentration times the hydroxide ion concentration, because those are our products, divided by the reactant concentration, which is the concentration of ammonia at equilibrium. We're then going to replace this with our equilibrium line. So our two products are going to be X times X. So we can go ahead and say that this is equal to X squared divided by the reactant, which was the ammonia, which at equilibrium is NH3 initial minus x. And let me extend this here. And we do know the value of KB. KB was given to us in the problem as 1.8 times 10 to the minus 5. All right, so we have one equation for which we have actually a set of two unknowns. We don't know X and we don't know the initial ammonium concentration. The initial ammonia concentration is actually what we are looking for, right? That's what the question is. So we need to have another way to find X. And this is where we come back to the pH. We said that from the pH, we could calculate the pOH. From the pOH, we could calculate the hydroxide ion concentration at equilibrium. And at equilibrium, the hydroxide ion concentration is equal to X. So that means that once we have this, we actually do have X. So let's go ahead and work on this on the side and see if we can get the value of X. So first of all, how do we find pH from pOH? We know that the pH is going to be equal to 14 minus the pH, which is 11.17, and that gives us a All right, so we know that the pOH is equal to 14.00 minus the pH, which is 11.17. That gives us a pOH that is equal to 2.83. From there, we know that we can find the hydroxide ion concentration by doing 10 to the minus pOH, which is equal to 10 to the minus 2.83, from which we get the concentration as 1.5 times 10 to the minus 3. 1.5 times 10 to the minus 3 molar. In terms of the significant figures, remember that if you have two decimal places on the pH or the pOH, you're going to end up with two significant figures on the concentration. And then remember that that value, the hydroxide ion concentration, is actually equal to X, because the hydroxide ion concentration at equilibrium is equal to X. So now that we have that X, we're actually going to come back to this equation, put it in the X boxes here and here, and we're going to do a little bit of algebra, solve for the ammonium ion concentration, for the ammonia initial, and be able to solve for it. So in this particular case, I'm going to rearrange the equation and I'm going to say, okay, my NH3 concentration initial is going to be equal to X squared divided by the KB value, which was the 1.8 times 10 to the negative 5. And then that is going to be plus X. Plug in the value of X here and here, and you should be able to get your answer as 0.13 molar. And we are done. Yay! All right, hopefully you guys understood that. I did skip a couple of steps here on the algebra, but I hope that you guys are able to do that yourselves. All right, next example. This is a little bit, actually this is one that you guys are going to do at home. I'll go ahead and give you the solution so that you can check to make sure that you got the same answer. So, all right, the answer to part A is, let's see, we're calculating the concentration, and that gives us 1.0 times 10 to the minus 2 molar. And then for the second part, the pH of the solution, you should get the answer as 12.00.